Hello, my name is Bing Wang. I'm going to talk about DataPlanner, data budget-driven approach to resource-efficient ABR streaming. This is joint work with Yan Yuanqing, Chinmei Shende, Chunjin Park, and Shu Guosen. Video streaming in cellular networks has been increasing at a remarkable rate, as shown in Cisco's global mobile data traffic forecast in this figure. We know video streaming is data-intensive. This is particularly an issue for cellular networks, since cellular network bandwidth is a scarce resource. The question is how to reduce mobile data usage while not impact users' QoE. We focus on adaptive bitrate or ABR streaming, the de facto technology in industry. In ABR streaming, the server stores multiple versions of video called tracks. Different tracks have different quality and bitrate. Each track is divided into multiple segments, each a few seconds long. The client uses adaptation logic to dynamically decide which segment to fetch during the playback to adapt to dynamic network bandwidth. We focus on video on demand service, which is a popular ABR streaming service. Two data-saving approaches have been used in industry. One is network-based. That is, based on user preference, network operator may cap network bandwidth. The second is streaming service-based. That is, the player app provides multiple options, for example, good, better, best options in Amazon Prime app for user to save data. In the research literature, most ABR schemes aim to maximize quality, except for one work that selects segments based on user-specified target quality, which can reduce data usage. The existing approaches have limitations. They do not provide users explicit control of data usage. They do not consider the overall data usage in the ABR logic, and it's difficult for them to achieve good balance between quality and data usage, considering that videos differ in genres, encoding, and complexity. In this paper, we explore a new direction that is based on users' willingness. We specify a data budget for streaming a video in a session, and then we develop quality-aware ABR schemes given the per-session data budget. This approach can explicitly constrain the total data used in a session. Users can decide the data budget, and the player rations data usage and guides the ABR logic across a session to adhere to the overall data budget. We call this approach data budget-driven ABR streaming. Our goal is to design data planning strategies so that the total data consumed is no more than data budget D, and the strategies steer the selection of the tracks towards good QoE. In addition, the strategies should work in conjunction with existing ABR streaming ecosystem so they are easy to deploy. The challenges of designing such strategies are twofold. First, we need to satisfy the data budget while not impacting user QoE much. Second, we need to account for diverse video characteristics in terms of genres, encodings, complexity, quality variabilities, and so on. Before presenting our technique, I first describe a simple Strawman strategy, which just finds the highest track so that its corresponding size is no more than the data budget D. Then it caps the segment selection to be no more than that track. This cap track strategy is similar to what is used in commercial practice. It has two major drawbacks. First, it can lead to a highly variable quality even under high network bandwidth, as shown in the beginning and end of the middle figure, since the segments in the same track can have very different qualities. For example, segments with complex scenes have lower qualities than segments with simple scenes. Second, it does not use leftover data budget effectively, causing underutilized data budget and lower QoE than what can actually be achieved. One example is shown in the bottom figure. In the middle of the session, since the network bandwidth is low, the player has to choose a lower track, which leads to a lower data usage than what is anticipated. When the network bandwidth becomes high later on, the Strawman strategy still caps the top track to the original value. As a result, a lot of data budget is left at the end of the session as shown in the red curve. The blue curves in the middle and bottom figures illustrate the results of the strategy that we propose, which I'll describe next. Our strategy is called DataPlanner or DP. This figure shows the input to DP and its interaction with ABR logic. DP keeps track of data usage and replans periodically. For example, every delta seconds or after n segments have been downloaded. Each time, it decides the target track for each remaining segment position so that the selected track is no more than the target track. This picture illustrates the advantage of DP over the simple strawman strategy. First, because DP decides the target track for each segment individually, it can lead to smoother quality. Second, since DP replans periodically, it can better account for changing network dynamics and lead to better usage of the data budget. We developed two DP strategies, one called DPQ for the case where per segment quality information is available. Here Q represents quality. The second is DPT for the case where per segment quality information is not available, so we only use track information. Here T represents track. Both strategies run periodically. Each time a strategy runs, it considers per segment size of the remaining segments and the remaining data budget. It can either interact with the ABR logic beforehand by restricting the set of tracks to be selected or afterwards to cap the selection of the ABR logic. Neither strategy considers network bandwidth prediction since the prediction is short-term and is already considered in the ABR logic. This picture illustrates how DPQ works. It shows a video with 3 tracks, blue, yellow, and orange. For each track, the colored curve on the top represents the corresponding quality of the segments in the track. We see in the same track, the 5th segment has much lower quality than other segments, maybe because it has more complex scenes. DPQ finds the target quality Q star, which is the highest quality that can be supported under the current data budget. In the figure, the horizontal black line represents the target quality, which can be found using binary search between the lowest and the highest quality. For each segment, DPQ then determines the highest track that is below the target quality, which we call target track. In this example, the target track for the 5th segment is track 3, while the target tracks for the other segments are either track 1 or 2. As a result, the 5th segment gets a higher target track and more consistent quality as other segments. We now talk about DPT. In DPT, since per segment quality information is not available, we use track level to approximate quality. The idea is to determine the target track for each segment so that segments with complex scenes have higher target tracks. DPT identifies complex scenes based on relative segment sizes. Specifically, the segments with sizes in the highest quartile, referred to as Q4 segments, are regarded as those with complex scenes. In this picture, we illustrate 8 segments. Segments 5 and 6 are Q4 segments, and the rest are Q1 to Q3 segments. DPT first finds a base track for all segments. That is the highest track so that its corresponding size is no more than the data budget, just as the strawman strategy. If the data budget is not used up, then DPT increases the track level of Q4 segments by 1 in the playback order. If the data budget is still not used up, then DPT increases the tracks for Q1 to Q3 segments by 1 again in the playback order until the data budget is used up. In this figure, the base track is track 2. Since the data budget is not used up, DPT increases the track level for the 2 Q4 segments to track 3. After that, there is still remaining data budget, so DPT increases the track for segment 1 to track 3. Now I'll talk about performance evaluation. The goal is to understand the performance of combining DP with ABR schemes under diverse settings, including various ABR video characteristics, network conditions, and data budget. The methodology is to scale the data budget values and the network bandwidth traces relative to a reference track of video, which is chosen from the middle rounds that have fair to good quality in the track ladder. Specifically, the data budget is set to be the total size of the reference track times RD. The The average network bandwidth is scaled to be the average bitrate of the reference track times Rn, with variables Rd and Rn in a wide range. Our performance evaluation uses 100 LTE network traces, 4 H.264 and 3 H.265 videos. The performance metrics include quality of all segments, quality of Q4 segments, average quality changes per segment, total rebuffering, and data usage. We use VMAF, a state-of-the-art perceptual quality metric, to measure quality. VMAF values are from 0 to 100. The higher, the better. We consider 3 state-of-the-art ABR schemes: robust MPC, Kava, and the default ABR logic in Axel Player, which is a very popular player for the Android platform. The 3 DP strategies are DP Strawman, which is the simple Strawman strategy used as a baseline, and DPQ and DPT that we develop. We first show the results of DP with robust MPC. These 5 figures plot the CDFs of the 5 performance metrics. In each figure, we show the performance of the 3 DP schemes with robust MPC and the original robust MPC scheme. We see that DPQ and DPT lead to significantly lower data usage than the original robust MPC scheme, while have similar amount of low-quality segments as robust MPC. DPQ and DPT achieve much better quality than DP Strawman, as shown in the top left and bottom left figures. Last, DPT leads to similar performance as DPQ. This slide shows the performance of DP with Kava. We see similar trends as DP plus robust MPC in the previous slide. We also implemented the 3 DP schemes in Axel Player and instrumented Axel Player to record detailed information about the ABR streaming process. The version of Axel Player that we use combines segment replacements and the ABR logic. Since we are seeking opportunities for achieving good QoE under strict data budget constraints, we disable segment replacement and leave the issue of DP with segment replacement as future work. Our experiments show that both DPQ and DPT are lightweight. The total running time is around 50 milliseconds for over 100 segments. These 5 figures show the CDFs of the 5 performance metrics when using DP with Axel Player. We see that using DPQ and DPT leads to significantly lower data usage and less rebuffering compared to the original ABR scheme in Axel Player. Last, DPT and DPQ significantly outperform DP Strawman in quality. So far, we have assumed that per session data budget is given beforehand. We now sketch one possible approach that determines per session data budget choices for specific video as illustrated in this figure. The bars on the left represent the track sizes. We first roughly decide the quality levels based on the tracks. Then we determine a data budget ladder shown by the light blue bars on the right. In this example, the lowest rung in the data budget ladder, that is low data usage, poor to fair quality, maps to data usage between track 2 and 3. The second lowest rung, that is medium data usage, fair to good quality, maps to data usage between track 3 and 4. Other rungs are defined in similar ways. The key point is that each rung in the data budget ladder represents a range, as RD times size of track I, where RD is larger than or equal to 1. This range provides flexibility. For example, for more dynamic video, RD can be set to a larger value, while if the remaining monthly data budget is low, RD can be set to a lower value. The streaming service can consider the multiple factors and determine the specific data budget for a particular session appropriately. To conclude, we proposed a novel DP framework for ABR streaming with a per session data budget. This direction provides users a knob to directly control the data usage. It is modular and incrementally deployable. We developed 2 strategies, DPQ and DPT. DPQ is suitable for the cases where per segment quality is known. DPT works when such information is not available. Our extensive evaluations show that per-session data budget plus carefully designed DP strategies can significantly lower data usage while still delivering good QoE. Thank you.